Hello everyone, this is Lakshmi BR from Jawaharlal Nehru Planetarium, Bengaluru. So today I want to discuss with you people astronomy as a gateway to teach trigonometry. Yeah. So when we introduce trigonometry to our students for the very first time, the first problem we as teachers and our students face is that the topic will be very new to them. So to overcome this problem, the very first thing that we can do is not to introduce this as a new topic, but rather bring in trigonometry as an extension of the ideas that they have already learned in their classes on triangles and circles. Okay. And another thing that we can do here is bring in some real life situations, real life examples with which our students can easily relate to. And one such set of real life situations is astronomical examples. Okay, so examples from astronomy play a very important role in taking trigonometry very close to our students. So one of the methods that we discuss with our students in our trigonometry classes is finding the heights and distances, right? That's again a different chapter in trigonometry. But even there, we can bring in real life situations like measuring the height of the tree with nothing more than a stick. They would have actually given many problems where the angle of elevation is given and the distance is given, and then they're asked to calculate. But just doing the calculation that way will not be that very fun. Rather than that, give them a stick which is having the same length, which is equal to their arm length, and then ask them to go very close to the tree. Just hold the stick as it is shown in the diagram here. So you can see here, the girl is holding the stick there, okay, at one arm distance, and then start moving away from the tree. And stop at a point where the tip of the stick and the tip of the tree are exactly in line. So by doing that, what we would have achieved is we'll be having a pair of similar triangles, and these triangles will be isosceles because we took the stick length same as our arm length. So that is an isosceles triangle there, and the tree, the distance to the tree and the height of the tree, those two will also be the same. So this will be a fun way of doing the same exercises that we usually do in our trigonometry classes. But then we don't have to stop at that. We can extend our discussions to the sky. Okay, so we can bring in examples like measuring the altitude of moon, or measuring the altitude of any particular star in the sky. And this can be done by using the concept of angular sizes or angular measurements. What we do in angular measurements is actually expressed here in one of the pictures. You can see here this person has stretched his arms, okay, and he has completely wide opened his fingers like that. So this entire stretch kept at one arm distance will be subtending an angle of 20 degrees at our eyes. And with this single finger, which is stretched at one arm distance, that will be subtending an angle of 1 degree. And if you just hold your fist like that or like this entire measure, that measures out to be something like 10 degrees. So we can use our hand as a tool to measure the angular distances or angular separations in sky. Okay. This is very much similar to some of the examples that we solve in our trigonometry classes. I have also given some examples of angular size of moon and the angular separation between these first and second star of the Big Dipper, and the angular separation between these two stars of Southern Cross. So likewise, we can include many other examples from the sky and make this a very interesting exercise. Now, when we are talking about angular size, the way we draw pictures really matters. And you can see here, I have put 3 different diagrams, and all of them have got this angle here, that is the angular size. So let us say this is some object. For example, I have taken here moon as the reference object. So if this is the moon, I am drawing a diameter here and I am observing the moon from this point. So this is the observer, there is the moon. I'm sorry. So there is the moon. So there is an angle alpha subtended at the eye of the observer. We say that is the angular diameter of the moon. Instead of having an entire circle there, so in this diagram, there is just a line represented there. That's the diameter, real diameter of the object. But it is subtending an angle theta here. But what is the major problem with these two pictures, figure 1 and figure 2? The major problem is that there is something conceptually very much wrong there. So we are considering our right angle triangles using tan theta definition to find the radius if the distance is known, or the distance if the radius is known. We do that. That's a common thing that we do in our classes. But having said that this is a right angle triangle, where should be the right angle formed? See, in this figure 1, it is denoted here, which is conceptually wrong, because this is supposed to be, this part is supposed to be the radius, right? And this line, what is drawn from the observer, that is supposed to be the tangent. And there is a circle there. So there is a radius, there is a tangent to the circle. We know by the ideas that we know about circles that these two, that is the tangent and the radius, they'll have to be perpendicular to one another, which is not shown in this diagram. So even when we are drawing our diagrams, we should be very careful that we should not be giving any misconception. If you come to this diagram here, the third one, yeah, see, the D of this sun that is shown here is bent this way. It is one radius there, another radius here. So two radii put together gives your diameter, that is for sure. But conceptually, what we are showing here is that the radius and the tangent, they are they are perpendicular to one another. So that concept should not be left out. Okay. Then once they're introduced to measuring the angular sizes this way, and bring in tan theta to find either the radius or the distance to the celestial objects, that becomes a very handy tool. And then we can ask them to find the angle of elevation of not the pole or the tree, but of some inner planets like Mercury and Venus. Venus, none of us can miss, right? So we can actually ask them to repeatedly observe what is the greatest angle Venus can reach in the sky. With their observations, they will get to know that it can be something between 45 degrees and 47 degrees. Okay, so after knowing this greatest elongation can be something like between 45 degrees and 47 degrees, they can actually figure out, so that is alpha, which is known to them now. So they can figure out this r, which is the distance to the Venus from the sun, just by using the definition of sine alpha. Because sine alpha is what? Opposite by hypotenuse. And hypotenuse is one astronomical unit. So that is unity now. So r will be equal to sine of alpha. So again, we'll have to remember that this angle EVS should be the right angle in our right angle triangle, and not this other angle VSE. Okay, so right angle has to be formed there because that is the tangent and this is the radius. So again, here we have approximated the orbit to be a circle, but in reality we know that it is not a circle but an ellipse. But that part also can be figured out by continuing the same activity of measuring the greatest elongation of that particular inner planet. Okay, and the very fact that there was a range for the greatest elongation, say between 45 and 47 degree, that itself will be actually giving us a hint that the orbit cannot be a circle, but it has to be a ellipse. So here in this animation, it is shown that how we can actually trace out the orbit of a inner planet, okay, just by using the measurements of greatest elongations. Okay, yeah. So this was about finding a nice activity to enjoy the concept of angle of elevation. But what about angle of depression? That also we do teach in our trigonometry classes. So here is a wonderful example to make your angle of depression a very interesting idea. Okay, so here I have given Alberoni's method of finding the size of the Earth. Okay, I'm sorry. What Alberoni basically did is he actually went to the top of a mountain, and the height of the mountain was known to him. So that's the mountain M. So top of the mountain is designated as M here in our picture. So he knew the height of the mountain, which is small h. Okay, and from there he measured the angle of depression for horizon. Okay, so horizon, you can see it's here. So this line is horizon. So he measured this angle of depression delta for the horizon. And then with simple geometry, he could actually figure out that this angle delta, which is formed here, sorry, so this angle delta, which is formed here at the center, so this also has to be delta, can be figured out with just simple geometry. And then just by defining cos of this angle delta, he could actually get what is the radius of the Earth. So here you can see a plus h there. A is the radius, but h is the height of the mountain. So just by defining cos delta and a little bit of simplification, he could actually figure out what is the radius of the Earth because he knew the height of the mountains, small h. Okay, so likewise, bringing in these examples from astronomy into trigonometry will be really, really helpful. These are just some one or two examples that I have shared with you people, but there are a lot more which can be actually brought into our trigonometry class. And by doing that, we would have actually taken trigonometry very much closer to our students. It will not remain as something very new, very unknown to them. So we can actually bring in these ideas of circles and triangles, whatever they have already learned, while discussing our trigonometry concepts. So that will be like taking them from the known towards the unknown. And then, of course, I can guaranteedly tell you that astronomical examples will really help us in making our trigonometry classes interesting and interactive. Thank you very much.